Welcome back to my channel. In this video, we are going to learn about binary number representation. Binary number can be represented as unsigned number or signed number. In unsigned magnitude representation, all the numbers are considered as a positive one. No negative number is represented by using unsigned number representation. And in signed number representation, we can represent both positive and negative numbers. In normal arithmetic operation, to differentiate this positive and negative numbers, we are using plus and minus sign. But in binary, all are represented by zeros and ones. So we cannot use plus and minus sign for positive and negative number. So here we have to use two different forms to represent the signed number. They are sign magnitude form representation and complement form representation. In this complement form representation, there is two types. One is 1's complement, another one is 2's complement. Let us see one by one. First one, unsigned binary number representation. Here all the numbers are considered as positive one. No negative number is represented in unsigned binary number. If your number has n bits, then all the n bits are used to represent the magnitude of that number. So the range of number which is represented in this unsigned binary number is, if the number of bits is n, then the range is 0 to 2 power n minus 1. For example, if there is 3 bits, using this 3 bits, you can represent 0 to 7. That is 2 power n is 2 power 3, 8, 8 minus 1 is 7. So you can represent 0 to 7 using this 3 bits. Let us see some examples. Here 12. 12 can be represented as 1100 in unsigned binary number representation. Here all the 4 bits are used to represent the magnitude. Next, 11001, the equivalent decimal number is, here all the 5 bits are used to represent the magnitude of that number. Here I mentioned the position weight. The decimal equivalent is 16 plus 8, that is 24, 24 plus 1, 25. So the decimal equivalent is 25. So in this unsigned binary number representation, we can represent one positive number. Next one, signed binary number representation. You can represent both positive and negative numbers using this signed binary number representation. There is 3 different forms available to represent positive and negative numbers. They are signed magnitude form, 1's complement form and 2's complement form. In all the 3 forms, the representation of positive number is same. Let us see one by one. First one, signed magnitude representation. So in signed magnitude representation, you have to add one more bit with the given binary number to represent the sign of that number. That bit is added in the most significant bit. In signed magnitude representation, the most significant bit, that is the leftmost bit of your binary number, represent the sign bit. And depending upon the sign bit, your number may be a positive number or negative number. For positive number, the most significant bit is 0. And for negative number, the most significant bit is 1. So for any number with n bit, the most significant bit represents the sign of that number and the remaining n minus 1 bit represents the magnitude of that number. Let us see some example. Here 11010, which is represented in signed magnitude representation. Here first bit, that is most significant bit, represents the sign of the number, that is 1, so the number is negative. Next, the remaining 4 bits represent the magnitude of that number. Here I mentioned the weight, position weight, 8 plus 2, 10. So the number is minus 10. Next one, 010101. Here the most significant bit is sign bit and it is 0. So the given number is positive. The remaining 5 bits represent the magnitude of that number. I mentioned the weight. So 16 plus 4, 20, 20 plus 1, 21. So the decimal equivalent is plus 21. In sign magnitude representation, for any number with n bits, first bit, that is most significant bit, represent the sign. The other n minus 1 bit represent the magnitude. So next example, represent plus 13 in signed magnitude form. The binary equivalent of 13 is 1101. Here it is a positive number, so the most significant bit is 0. So you have to add 0 here to represent the sign. So this is the sign magnitude representation of this plus 13. So next one is minus 20. So first write the binary equivalent of this 20. Binary equivalent of 20 is 10100. Here it is a negative number. For negative number, most significant bit is 1. So you have to add 1 with this. So this is the sign magnitude representation of minus 20. Similarly, 32 in 8-bit can be represented as 00100000. Here 32 is expressed in 8-bit and the most significant bit represents the sign of that number. Here 32 is a positive number, so the most significant bit is 0. Next, minus 32 in 8-bit is represented as 10100000. Here the most significant bit is 1, which represents the given number is negative. The only difference between these two numbers is in the most significant bit. Next one is range of numbers. If the number consists of n bits, then by means of the sign magnitude representation, you can represent minus 2 power n minus 1 minus 1 to 2 power n minus 1 minus 1. For example, if you are taking n is equal to 4, then by using 4 bits, you can represent minus of 2 power 3 minus 1 to 2 power 3 minus 1. That is 2 power 3 is 8, 8 minus 1, 7. So you can represent from minus 7 to plus 7. Next, this table shows the sign magnitude representation of the given decimal number. Here we are using 4 bits. We all know that by using 4 bits, we can represent the number from minus 7 to plus 7 in sign magnitude representation. And here, one important thing is there is two representation for 0, that is plus 0 and minus 0. Here, the only difference between this positive number and negative number is at the most significant bit only. For positive number, the most significant bit is 0. And for negative number, the most significant bit is 1. In sign magnitude representation, the most significant bit represents the sign of that number and the remaining bits represent the magnitude of that number. So if you are taking plus 7, here it is a positive number. So the most significant bit is 0 and the magnitude 7 is represented by other 3 bits, that is 1, 1, 1. Same, if you are taking minus 7, it is a negative number. So the most significant bit is 1. The remaining 3 bits represent the magnitude, that is 7, 1, 1, 1. Next, we will see signed ones complement representation. Already I told you that in all the 3 forms, the positive number is same. For example, plus 7 is represented as 0, 1, 1, 1 in ones complement. The same representation is used in sign magnitude and also in 2's complement. But the representation of negative number is different. For example, if you take minus 7, first write down the equivalent positive number. So positive number means plus 7. So the equivalent positive number is 0, 1, 1, 1. Then to get ones complement, invert each bit in this positive number. That is nothing but replace zeros by 1 and ones by zeros. So now you get 1, 0, 0, 0. This is the ones complement representation of minus 7. Here look at this. Here it is positive number. Most significant bit is 0. Here it is the ones complement representation of minus 7. Here the most significant bit is 1. That is, it is a negative number. Let us see one more example. Minus 32. To find the ones complement representation of minus 32, first write down the equivalent positive number. That is plus 32. So plus 32, 0, 0, 1, 0, 0, 0, 0, 0. Next, to get the ones complement, invert each bit. Now you get 1, 1, 0, 1, 1, 1, 1, 1. So this is the ones complement representation of minus 32. Here the most significant bit is 1. It indicates it is a negative number. Here 0, it indicates that it is a positive number. So for any number, if you want to write the ones complement means first write the equivalent positive number, then invert each bit in that number. And the range of number that can be represented by this signed ones complement. If the number of bit is n, then the range of numbers are minus 2 power n minus 1 minus 1 to 2 power n minus 1 minus 1. For example, if n is equal to 4, then minus of 2 power 3 minus 1 to 2 power 3 minus 1. 2 power 3 is 8. 8 minus 1, 7. So by using 4 bits, you can represent minus 7 to plus 7. This table shows the signed ones complement representation of the decimal number. Here, the positive number representation is same as signed magnitude representation. Here, the most significant bit is 0. The remaining 3 bits represent the magnitude of that number. 7, so here 111. 6, so here 110. So it is same as signed magnitude representation. And here also there is 2 representation for zeros. That is plus 0 and minus 0. Negative number, the most significant bit is 1, which indicates that it is a negative number and it is different from sign magnitude representation. Next one is sign 2's complement representation. So positive number representation is same in all the 3 methods. So here also plus 7 is represented as 0, 1, 1, 1. Next one, we will see how to represent a negative number in 2's complement method. To get 2's complement, you have to add 1 with the 1's complement. Let us see how to find the 2's complement of the number minus 7. So first, get the 1's complement of this number. Then add 1 with that 1's complement to get the 2's complement. To get 1's complement, first write the equivalent positive number 0, 1, 1, 1. Then invert each bit. That is replace zeros by 1 and 1s by zeros. Now you get 1's complement representation of this minus 7. 1, 0, 0, 0. This is the 1's complement representation. To get 2's complement, you have to add 1 with this. If you are adding 1, you get 1, 0, 0, 1. So this is the 2's complement representation of the number minus 7. Let us see one more example. Find the 2's complement of minus 32 and you should represent this number in 8 bits. So first you have to find 1's complement. To find the 1's complement, first write the equivalent positive number 0, 0, 1, 0, 0, 0, 0, 0. Next, to get the 1's complement, invert each bit. So you get 1, 1, 0, 1, 1, 1, 1, 1. This is the 1's complement representation of this minus 32. To get 2's complement, you have to add 1 with this. So now 1 plus 1, you get 0 with carry 1. Again 1 plus 1, you get sum 0, carry 1. 1 plus 1, sum 0, carry 1. Again 1 plus 1, sum 0, carry 1. 1 plus 1, sum 0, carry 1. So now 1 plus 0, you get 1. Here 1, so you get 1. And here 1, you get 1. So this is the 2's complement representation of minus 2. So 2's complement representation of minus 2 is 1, 1, 1, 0, 0, 0, 0, 0. Next one is range of number that can be represented by this 2's complement representation. If the number of bits is n, then the range of numbers that can be represented by this method is minus 2 power n minus 1 to 2 power n minus 1 minus 1. For example, if n is equal to 4, then 2 power 3 to 2 power 3 minus 1. That is minus 8 to 7. So by using this 4 bits, you can represent the number from minus 8 to 7. This table shows the signed 2's complement representation of the given decimal number. Here, the positive number, representation of positive number is same as sign magnitude and 1's complement. And there is only one representation for 0. And by using this 4 bit, you can represent from minus 8 to plus 7 using this signed 2's complement representation. So in next table, I will combine all the 3 representation. Here, the representation of positive number is same in all the 3 representation. And its sign magnitude and signed 1's complement representation, there is 2 different representation for 0. And in this 2 representation, you can represent minus 7 to plus 7 using this 4 bits. And in 2's complement representation, there is one representation for 0. And by using this 4 bit, you can represent from minus 8 to plus 7. Thank you for watching.